So in this video, we'll talk about elliptic curves, and this is like an introduction to elliptic curves in cryptography. Today, we'll just focus on the basic definitions needed for our elliptic curve study. So it is very useful to see this in two lenses. Basically, one lens is geometry and the other one is algebra. And this is basically where algebra and geometry meet, so that's really nice. And we're gonna basically divide this table into two sections. One is basically the algebraic representation of this elliptic curve over here. All right, so we're going to basically compare the geometric representation to the algebraic representation. If you've seen any elliptic curve, you might be familiar with this shape over here. All right, it has nothing to do with ellipses, by the way. So in geometry, if we were to draw an elliptic curve, we call it a plane curve. That's because this curve exists in a plane, basically an XY plane. These are the XY axes, right? So it exists in a two-dimensional plane. So that is pretty much an elliptic curve. It has usually this form. It has also other shapes and forms as well. Now, the most common representation of this curve is captured here in this algebraic equation. An equation in algebra is anytime you see this equal sign. Now, there are two ways to represent an equation. Either you can set one variable on one side and the other variable on the other side. Here we're using x and y. So you see y on one side and all the x's on the other side. Another common way to write an equation is to put everything on one side and the zero on the other side. I mean, even if you wrote any other constant, you can always move it and keep the zero on that side. So maybe people are more familiar with this as an equation. We call it a variable in two equation because you have these two variables all together in one side. If you're plotting a curve, usually you see this form where we separate the y from the x, again because geometrically x is one axis and y is the other axis. Sometimes we call them domain and range. And usually it's written as y equal f of x. All right. Now the other form is to write it like this, to say that the general form of this is fxy equals 0. All right. And what it is actually, if you look on one side, you have a polynomial. Okay. So this is a polynomial, again, in two variables. Because you can write a polynomial with just one variable, but here the polynomial has two variables, x and y. Now, every polynomial has a degree, and the way to determine a degree is by looking at the highest power, that exists in here. And the highest power here is 3. So this is a polynomial of degree 3. And that's by definition, every elliptic curve, okay, has a degree of 3. This is the only degree we deal with when we talk about elliptic curves. So that is very important. Keep that in mind, that every elliptic curve will be based on a polynomial of degree 3. And that is the highest degree you can find in this polynomial. The other important element here is the coefficients. So these are the coefficients a and b. I wrote them in different colors so you can separate them from the rest. So these two coefficients act like a knob when it comes to elliptic curves, because every time you change a and b, the shape of the curve will change. I mean, the overall look is still the same, but the shape could change, like the curve could open up or could close to a point sometimes where you have a circle separate from the other curve. So it's A and B that are basically changing the shape of the curve. So every time we come up with a different pair of A and B, we're basically going to come up with a different curve here. So that's the role of A and B. A and B usually belong to a field. So, and that's to make sure that we have closure. We can talk about that later when we talk about, you know, more details related to the variables and to the parameters. But just keep in mind that for now that A and B belong to a particular field. Now, another thing to keep in mind is that every equation has solutions, all right? Now, what does that mean geometrically? Okay, now every point on the curve, remember, every point on the curve is actually a solution to this equation. Okay, so every pair, so every point on the curve is nothing but an xy pair, right? Every point has a coordinate. You know, we're working with a coordinate system, so it has two coordinates, x and y. Right? Now every pair, every point on this curve is made of this pair x and y, and it will serve as a solution to this equation. All right? Everything that is not on the curve will not be a solution to this equation. So obviously the number of solutions is far less than the overall number of points in the plane. People from a long time ago, like mathematicians, were obsessed in finding special solutions to equations like these. So obviously, if you're looking for all the real solutions, right, then there'll be an infinite number of solutions because this curve will go for infinitely, right? It will go to infinity both ways. But what if we were looking for special solutions like the set of all integers that are solutions that exist on this curve? That is not very obvious, right? Or we're looking for all the rational solutions. That's a more common thing to do, right? So if we're looking for all the rational solutions, right, for this equation, so these are not easily determined, and it takes a bit of, you know, intuition and also some work, right? The next thing to look at is, if I were to draw a line, and here I drew it in green so that we can separate it from the actual curve. If I were to draw a line that intersects this curve, right? How many points of intersection would I usually get? And that's very neat because usually, again, satisfying certain conditions, the number of points that intersect the curve will always equal to the degree of this polynomial. Okay, so again, since we're talking about elliptic curves, the degree, as we said, is 3, and hence anytime you draw a line through the curve, you're going to have 3 points of intersection. Now this is going to prove very, very useful later because 3 is a very special number in math in general, right? Remember, anytime we write any operation, like a binary operation, it's going to have 3 elements: x, for example, y, and equals z, right? So you have, this is called a binary operation, right? This is the operator. It could be anything. In abstract algebra, you know, it could be any type of addition. Doesn't have to be the arithmetic addition, right? But anyway, we have basically 2 elements here that lead to a third element. All right, that's going to prove very important later. So degree 3 is so special because usually in operations we have 3 elements, right? And 2 elements will yield the third one through some form of operation. Likewise, as we're going to see later, we can start with 2 intersects, right? And those basically represent these 2 elements here. And then through some magic, some operator, we will be able to obtain the third element. And what is neat about it is that this third element will always belong to the same group that these two elements belong to. That's what closure is. So likewise, we see that geometrically happening. This is why 3 is a very special number, because it basically looks like any operation we do within any group, ring, or field. And this is basically what we're going to discuss in the next videos.